Gnanam paramam dheyam. Knowledge is supreme.
So, let us begin today's lecture. We will start recalling what we have been doing. We have been looking at the definition of eigenvalues, eigenvectors and diagonalization of matrices. So, let us just recall the example we had done. We had taken a matrix A as shown with first row minus 5 minus 7 and 2 and 4, and we showed that it has two eigenvalues lambda equal to 2 and minus 3. For each one of these eigenvalues, we found eigenvector C1 is the eigenvector for the eigenvalue 2 and C2 is the eigenvector for the eigenvalue minus 3. And finding these eigenvectors is essentially solving a system of linear equations. So, and this gave us the matrix P with first column as the first eigenvector, second column as the second eigenvector. And this we showed that since these are eigenvectors corresponding to distinct eigenvalues, these two vectors are linearly independent, and as a result this matrix P has got full rank, so it is invertible. And then we check the property that P inverse AP is a diagonal matrix, and the diagonal being the eigenvalues 2 and minus 3. So, this was the illustration of how to find a matrix which will diagonalize a given matrix A. So, this prompted us to define and ask the question, given a matrix A, when does there exist an invertible matrix P such that P inverse AP is a diagonal matrix, and how to find that P. So, we made a definition that a matrix A is diagonalizable if there exists a matrix P which is invertible such that P inverse AP is a diagonal matrix. And we stated a theorem, actually we proved it also partially. So, let us just go through the proof again. If A is a n cross n matrix, then A is diagonalizable if and only if. So, this is a if and only if statement. There exists scalars lambda 1, lambda 2, lambda n and vectors C1, C2, Cn such that the following holds. 1. A applied to the vector Ci is lambda I Ci, and this essentially says that the scalar lambda I is an eigenvalue and Ci is an eigenvector for the eigenvalue. And the diagonalizability is captured by the fact that the set of these eigenvectors C1, C2, Cn is a linearly independent set and hence forms a basis for Rn. There are n vectors which are linearly independent and form a basis. So, let us just run through the proof again. So, suppose P is A is diagonalizable, then there is a matrix P such that P inverse AP is the diagonal matrix. So, there is a invertibility implies there is a matrix P with this property. So, let us call C1, C2, Cn the columns of that matrix P, right. So, P is given by C1, C2, Cn. Since P is invertible, then none of these vectors could be 0, because all the vectors are they form a linearly independent set. So, none of them is 0, and in fact being an invertible matrix has a full rank, right. So, they are linearly independent. So, let us define D to be the matrix with the diagonal entries as lambda 1, lambda n, everything else as 0. So, we are defining D as this, and we want to check that these are the lambda 1, lambda 2, lambda n are eigenvalues. We want to check that D is given to us. We are given P and we are given D. So, D is given to us, this is D, and C1, C2, Cn are the column vectors of P. So, we want to check that lambda 1, lambda 2, lambda n are the eigenvalues and C1 to Cn are the corresponding eigenvector. So, for that we just rewrite this equation P inverse AP equal to D. slightly differently. So, the matrix multiplication, this implies if I multiply both on the left by p, then AP is equal to p times d, and let us write p and d in terms of the columns. So, p is column as C1, C2, Cn. So, this value is put here into d, and what is this multiplication? That is precisely writing it as the columns being AC1, AC2 and ACn, and this being the diagonal matrix, these columns are lambda C1, lambda 2 C2 and so on, right. So, this is just matrix multiplication, nothing more than that. So, this is equal to this, that means AC1 is equal to lambda 1 C1, AC2 is lambda 1, lambda 2 C2 and so on. So, in general the jth entry ACj is lambda j Cj, and that precisely says that lambda j is an eigenvalue with Cj as the eigenvector. So, one way is done. So, conversely let us suppose that we have got elements vectors x1, x2, xn such that is a linearly independent set, and this lambda i's are the corresponding eigenvalues. So, Axi is equal to lambda I xi. So, that is given to us, right, the property. So, what we want to show? We want to show that there is a matrix P such that P inverse AP is diagonal. So, let us construct the matrix with these as the column vectors, right. So, P is defined as with these vectors as the column vectors. So, these being linearly independent, so it is a linearly independent set. So, this is invertible, right. So, rank of P is n, it is an invertible matrix. So, we can compute now what is AP, and that comes out to be, right, AP is, write the column 8 times the column vectors of P x1 xn, that is the same as Ax1 Axn, and using the property that Axi is lambda I xi, this comes out, and that is precisely P times d. So, d, if we write d as a diagonal matrix lambda 1 to lambda n, then we get AP is equal to P times d. P is invertible, so that can be written as P inverse AP is, right. Just writing, there is nothing in the proof except that writing the matrix multiplication A times P as A times the column vectors and expressing it appropriately. So, this proves the theorem that a matrix A is diagonalizable if and only if there are n eigenvalues, right, and there are eigenvectors corresponding to them form a linearly independent set. So, that is a condition for diagonalizability. So, the question comes, see in the so when they are linearly independent, everything is okay. So, the problem is given an n cross n matrix, how do you find a linearly independent set of eigenvectors, right. So, the question comes, does a given matrix have n eigenvalues 1, and for each eigenvalue you will have an eigenvector, do they form a linearly independent set or not? If yes, the matrix is diagonalizable. If not, you can't help it, it is not diagonalizable, right. So, basically what we are saying is this n eigenvectors will form a basis because there is in n cross n, right. So, saying that the matrix is diagonalizable is equivalent to saying finding n linearly independent eigenvectors for that matrix, right. And finding eigenvector means first you have to find the eigenvalues anyway. So, that is the problem we want to tackle. So, first of all there is an observation that supposing you have got lambda 1, lambda 2, lambda r are distinct eigenvalues of a square matrix. All the eigenvalues may not be distinct, right, they are the roots of the characteristic polynomial. So, roots can repeat, right. So, let us assume out of the n, lambda 1, lambda 2, lambda r are distinct eigenvalues of the given matrix, and V1, V2, Vr are the corresponding eigenvectors. So, then the claim is this set is linearly independent. So, what we are saying is even though all the eigenvalues need not be distinct, but if you collect the eigenvectors corresponding to distinct eigenvalues, they will form a linearly independent set, right. So, at least there is a some achievement, they may not be, all of them may not be distinct, but whatever are distinct, for each one of them you find an eigenvector. So, at least that many linearly independent vectors you have got, okay. So, let us prove this. So, let us assume, see this number is r, there are r linearly independent sorry r eigenvalues. So, let us assume that L, there is a number L less than or equal to this r with the smallest integers is that V1, V2, VL is linearly dependent set, right. Assume that there is a number L such that V1, V2, VL is linearly dependent. Okay. Suppose such a thing exists, okay. And let us pick up the smallest of them, right. That means what? If L is the smallest such that V1, V2, VL is linearly dependent set, then lesser one will be independent, right. This is the smallest, right, this is the smallest collection which is linearly dependent. So, if you take less, then that should be independent. So, that means that if we look at V1, V2, VL minus 1, that is a linearly independent set, right. So, that means what? So, there is this scalars not all 0, say that, see this is linearly independent. So, VL must be a linear combination of, right, because that is a dependent. V1, V2, VL is linearly dependent and V1, V2, VL is independent. That means VL must be a linear combination of the other one. So, let us write, so let us VL be equal to alpha 1 V1 plus alpha L minus 1 VL minus 1, where all of them are not, cannot be 0, right, because all of them are 0, then VL will be 0, okay, and that is an eigenvector. So, eigenvector cannot be 0, right, VL is an eigenvector. So, we have assumed that is an eigenvector. So, that cannot be 0. So, at least one of them is non-zero, alpha 1, alpha 2, alpha L minus 1, one of the scalars is not equal to 0. So, that is, let us keep that. So, let us multiply both sides by the scalar alpha L, then what you will get? So, alpha L VL will be equal to lambda 1 alpha L, right. Okay. So, what is A of VL? See lambda L VL, lambda L is an eigenvalue. So, what is lambda VL? That is equal to A of VL, right, because VL is an eigenvector for the eigenvalue, right, L lambda L. So, this is because this is an eigenvalue and VL is an eigenvector, but what is VL from this equation? That is a linear combination. So, we put this value here, okay, and use linearity of A. So, A times the sum is equal to sigma alpha I A of Vi, right, but A of Vi, again each Vi is again a eigenvector. So, what is this equal to A of Vi? That is lambda I of Vi, right, is it okay? So, the first equation is because VL is an eigenvalue and from 1 this value is put here, right. So, A of the summation and then by linearity this is sigma alpha I A of Vi, and each Vi being eigenvector, this is nothing but lambda I of Vi, okay. So, let us keep this equation as 2. From this equation also I can multiply both sides. If I multiply both sides by lambda L, what is lambda L VL? That is alpha 1 lambda L V1 plus alpha L minus 1 VL L minus 1, right. So, I can multiply this equation also both sides by lambda L, I will get another value of lambda L VL. So, these two must be equal then after multiplication, right. So, multiply this by lambda VL to get the next equation. So, lambda L VL is equal to that. So, from the 2 and 3, if I subtract the two equations, right, both give me value of lambda L VL, right. So, this is lambda L VL as equation, this is one value and the other value is this. So, subtract the 2, you get 0 is equal to alpha I, that is a scalar comes out, lambda L minus lambda I Vi, I equal to 1 to L minus 1, right, subtracting the two equations, that is all. Now, I know that Vi's are linearly independent and this is a linear combination which is equal to 0. So, that means what? All the scalars must be equal to 0. So, alpha I lambda L minus lambda I must be equal to 0, but at least one of the alpha I is not equal to 0, right. That means for that particular I, lambda L minus lambda I must be equal to 0, if that product has to be 0. That means for that particular I, lambda L will be equal to lambda I, but that is not possible because they are distinct. So our assumption must be wrong, right. So that is what we are saying. So by linear independence, all these scalars must be 0, but for some alpha I is not 0. So that means for some I, lambda I must be equal to lambda L, which is a contradiction because all are given to be distinct. So that means what? That means we assume there is a L, say that V1, V2, VL is linearly dependent. That means that such a thing does not exist. That means all of them are linearly independent, right. So the theorem says that if lambda 1, lambda 2 are distinct eigenvalues of a square matrix, and you pick up an eigenvector for each one of these eigenvalues V1, V2, Vr, then that is a linearly independent set. That means the eigenvectors corresponding to distinct eigenvalues are linearly independent, right. That is a, so in case you have all eigenvalues are distinct, then you will get n linearly independent eigenvectors. You are very lucky. Okay. If not, then the problem can come. So the problem can come if the characteristic polynomial has multiple roots, right. A root is repeated, right, and for that particular eigenvalue you may be able to find one or two eigenvectors, we do not know, right. So let us look at an example. So let us look at the example of matrix A 1 1 0 1, right. So how do you find the eigenvalues? This is A minus lambda I, determinant is equal to 0. So that will give you 1 minus lambda 1 0 1 minus lambda, determinant of that will be, right, t minus 1 square if t is the variable you are introducing, if lambda, then lambda minus 1. So that means what? So there is only one eigenvalue, right, and that has got, it is repeated, right. So there is one eigenvalue t equal to 1 and that is repeated. Okay. So let us find the eigenvector corresponding to that eigenvalue. So how do you find the eigenvector? So look at the eigenvalue. What is the eigenvalue? T equal to 1. So A minus lambda I, right. So what is A minus lambda I? 1 minus 1, that becomes 0. Okay. 1 minus 1, that becomes 0. So everything is 0 except the second entry in the first row, right. So that is A minus lambda I for lambda equal to 1. So what this itself is in reduced row echelon form, we do not have to do anything, right. So what is the rank of this matrix? We want to solve homogeneous system A minus lambda I applied to x is equal to 0. We have to find solutions to find eigenvectors for that, right. So for that we have to know what is the rank of this. So rank, what is the rank of this matrix? That is 1, right. So rank is 1. So what is nullity? That is equal to 1. Rank plus nullity equal to the dimension, right. So nullity means what? For the homogeneous system, that is the dimension of the solution space. So dimension is 1. That means there is only one linearly independent eigenvector for the eigenvalue lambda equal to 1, right. We can find that. So how do you find that? So this applied to x1 x2 is equal to 0, right. So what does it mean? You can give x2 any value, right, 1. What is x1? You can give it 0. So you get 1 0 as solution for this space, right. So is a one dimensional. So this the solution space of A minus lambda I, lambda being 1, is of dimension 1, and you get a vector for this which spans this one dimensional. So 1 0, right, that is one of the vectors. So there is only one eigenvalue and that is repeated, but there is only one eigenvector. So that means what? I cannot find a basis of R2 consisting of eigenvectors, right. So what does the previous theorem tell me? This matrix is not diagonalizable, right, because there is only one eigenvalue, and for that eigenvalue lambda equal to 1, I can find only one linearly independent eigenvector, because the solution space has got dimension 1, right. So, it depends on, for a root, if it is repeated, can I find that many linearly independent eigenvectors for it or not, right. Essentially it boils down to that. So, let us give some names to these things. So, for the null space of A minus lambda I, that is a solution space, we will start denoting it as E lambda, that is the eigen subspace for the eigenvalue lambda, right. All the vectors which form a solution for A minus lambda I equal to applied x equal to 0, right. So, that is a null space of that matrix, we are given different names. Okay. So, we will start calling, if lambda is an eigenvalue, that means it is a root of the characteristic polynomial, and root may be repeated. So, the number of times it is repeated, that is called the algebraic multiplicity of that eigenvalue. So, as a root of the characteristic polynomial, it will be at least appearing once, because it is a root. It may appear twice, thrice, or so many times. So, number of times it appears, that is called algebraic multiplicity of the eigenvalue, right, and we denote it by m lambda. So, that is m lambda or m lambda of A, depending on if you want to stress that is a matrix A. So, that is the algebraic multiplicity. Now, on the other hand, for this eigenvalue, we are interested in eigenvectors, right. So, how many eigenvectors exist and how many exist, that depends on the dimension of the null space. So, that we call it as the geometric multiplicity of the eigenvalue. So, what is geometric multiplicity? That is the dimension of the null space of A minus lambda I n, right. So, that is same as the nullity of this matrix. Nullity gives the dimension. So, that is called the geometric multiplicity, and geometric multiplicity is written as G lower lambda or G lambda A. So, G for geometric multiplicity, m lambda for algebraic multiplicity, right. So, when do you think a matrix will be diagonalizable? There may be roots which are repeated, right, but if you count with multiplicity, there are n roots for a matrix of order n cross n. Some of the roots may be repeated, right, but for the roots which are repeated, the number of times it is repeated is algebraic multiplicity. Dimension of the null space of A minus lambda is geometric multiplicity. If as many independent you can find as the algebraic multiplicity, then you are through, right. Then you will have total number of eigenvectors will be linearly independent, and they will be n, right. So, if it is less, as happened in the previous example, lambda equal to 1 was an eigenvalue of multiplicity 2 algebraic, but geometric it was only 1. So, that was sort of the defect in diagonalizing the matrix, right. So, sometimes this number is called the defect for the matrix to be diagonalizable. If both are equal, then it will become diagonalizable, right, because for each eigenvalue you will have as many eigenvectors as is the algebraic multiplicity. So, put them together, you will have a linearly independent basis, linearly independent set of eigenvectors forming a basis. So, we can diagonalize that. Okay. So, that is what, so this is what normally called the defect, but that is not really important. Okay. What you call that difference. Okay. Algebraic multiplicity will always be bigger than geometric multiplicity. Is that clear? Yes. The number of times the root is repeated algebraically, that many eigenvectors you may not be able to find, you will be able to find only less of them, right, because they are independent. So, theorem says, if the algebraic and the geometric multiplicities of a matrix agree for every value eigenvalue lambda, then the matrix is, then there is a basis consisting of eigenvectors, right, and hence the matrix is diagonalizable, right. So, it is quite clear what is the proof. Basically, for each, if these are distinct eigenvalues with multiplicity m1, m2 and mk, right, for each we can find a basis, right, of as many as the algebraic multiplicity. So, find the basis and put all the bases together. For each eigenvalue there is eigenspace, there is a basis which has as many eigenvectors as is the algebraic multiplicity if they are equal. Put them together, you will get a basis consisting of eigenvectors for the underlying space Rn. Okay. So, their sum is equal to the degree of that is equal to n, right. Algebraic multiplicity equal to geometric multiplicity, total is equal to n. So, for each one of them there is a basis, put them together. So, there is nothing complicated in this theorem. Basically, that is how you will analyze whether a matrix is diagonalizable or. So, the main problem is, given a matrix, to show it is diagonalizable or not, what we have to do? We have to find for the given matrix what are the eigenvalues. Once you have found the eigenvalues, find out the corresponding eigenvectors, right. Find out the dimension of the corresponding eigenspace, that is same as the null space of A minus lambda I, right. If each is equal to the algebraic multiplicity, dimension nullity of A minus lambda I is equal to the algebraic multiplicity, then we are through. Then we can find a basis consisting of eigenvectors, right. These are just rewording the things. We say two matrices A and B are similar if A can be obtained by from B or B can be obtained from A by this process. B is equal to P inverse AP, where P is invertible, right. So, in terms of this, the diagonalizability can be said as a matrix, give any matrix A is similar to a diagonal matrix if and only if the algebraic multiplicities are equal to the geometric multiplicities, and we can find that. So, that is also the diagonalization process. So, it is a rewriting in terms of the terminology of when are two matrices said to be similar, because that is useful later on in other contexts also. So, for us it says that a matrix A is diagonalizable or similar to a diagonal matrix if and only if you can find an eigenbasis, that means find a basis consisting of eigenvectors, and that is same as for each eigenvalue the algebraic multiplicity is same as the geometric multiplicity.